In the last video for Unit 1, we're going to discuss transformations. So the main question that we're going to ask throughout this video is what happens when we manipulate f of x in a variety of different ways. We're going to do it in 3 different ways on this video, and then I'll briefly touch on a 4th way that we'll talk about later in the year. So if we have f of x, we can multiply f of x, we can add or subtract something to the x value on the inside of f of x, and we can add or subtract something to the entire function value later on. And as you'll see, we'll actually do examples of this later in a variety of different situations. The 4th thing that we can do is we can actually multiply the x value on the inside of f of x too. So we're going to answer what does A do, what does C do, what does D do, and then finally I'll talk about what B does briefly without any explanation, and then you'll just kind of have to trust me until we get to that part of the year where we can explore it more deeply. So let's take a look at the function y equals x squared. If I take a look at A, so A is multiplying my function, multiplying to my function. If I make A bigger, my function gets more narrow. And if I make A smaller than 1, my function gets wider. Essentially what's happening is it's changing my quote-unquote slope, so to speak. I know that x squared doesn't have a slope, but it's changing my rate of change. It's making y change faster when I increase A. It's making y change slower when I decrease it. If I make it negative, it flips and does the same thing. So the more negative it gets, the more narrow it gets. So that's what happens with A. With C, if I increase C, notice my function moves to the right. And if I decrease C, my function moves to the left. So it appears that C has some sort of shifting value for x, and D has a shifting value for y. So it either moves up or down based on what's happening. Also notice that we have x minus C on the inside. So when we were playing around with C, if I increase C, it's actually going to look like, in this case, where C equals 2, I will have x minus 2. So when I move C where it's x minus 4, that's actually going to be to the right. But if I have x plus 4, because x minus negative 4 would be x plus 4, that would move it to the left. If I take a look at x cubed, notice that A does something similar. It gets more narrow. As I increase above 1, it gets wider, grows slower as x or as A is smaller, and then there is a reversal or a flipping over the x-axis if it is negative. C, once again, does a horizontal shift, and D does a vertical shift. Now, can I do more than one of these things at a time? Yeah, I can have a vertical shift of 3 and a horizontal shift of whatever I want, 4, for example. And I can also decrease or increase what is happening with my vertical stretch, so to speak, which is the vocabulary that we'll use for the rate of change or the quote-unquote slope of something that is not a line. I can also do something similar with the square root function. Notice that I have vertical shifts, horizontal shifts, and it grows, the y grows faster or the y grows slower or I have a flip and the y grows slower or faster. So all of these things can happen. If I take a look at some function that is just kind of weird looking, I defined a pretty strange looking function. If I change a, things stretch. If I change c, they move left and right. It's a horizontal shift. And if I change d, it's a vertical shift. What does a do? A does a vertical stretch or shrink. So when a is greater than 0, it kind of looks its normal direction, and when a is less than 0, the graph flips. And when a is absolute value has a greater value than 1, that means that the y values increase more rapidly, which we will call a stretch. And if absolute value of a is less than 1, that means we have a vertical shrink. So the values increase less rapidly in that case. C is a horizontal shift, and D is a vertical shift. So they move functions right, left, up, or down, respectively. Now, one more time, I want to point out that in this case, we have f of x minus c. So for example, if I have f of x minus 2, this actually means I'm moving 2 to the right. So that means c is positive in this particular case. If I have f of x plus 4, that means I'm moving 4 to the left, because notice that a negative c value would make x minus c look like it's x plus 4 in that case. Whereas when I have a vertical shift, if I have something like f of x plus 2, that's going to move the graph up. And if I have f of x minus 7, that's going to move the graph down. And the reason why that's the case is that is a plus d at the end. Finally, this b value is a horizontal stretch or shrink, but we're not going to spend too much time on that right now. So just be aware that that's coming later in the year. First thing we're going to do in these examples is graph the parent function, and then we will graph the transform function and describe what happens. So y equals absolute value of x. If I remember what this looks like, I'm going to just plot some points. So it looks like a V. We remember this from yesterday, hopefully. Now if I take a look at 1/2 times f of x minus 3, notice that in this problem, f of x is equal to the absolute value of x. So I'm going to rewrite this as 1/2 absolute value of x minus 3, because I can replace f of x with the absolute value of x in this problem. That won't be the case in every problem, but in this particular problem, f of x is the absolute value of x. So if I plotted some points on this graph, if I plotted 0, I'd get -3. If I plotted 1, I would get -2.5 or -5 halves. If I plotted 2, I would get -2, and so on. So it would look something like this. After I plotted points, it seems like that's what happens. Now, if we take a look at what our notes said would happen, this 1/2 should end up being a vertical shrink. So essentially what happens is if I had a normal graph, the slopes were 1 and -1, depending on which side of the V I'm on. Over here, the slopes were 1/2 and -1/2, so plus or minus 1/2. So that means that I had a vertical shrink by a factor of 1/2. The other thing that happened was I have a -3. That is a vertical shift down 3, which makes sense. Notice what happened to my vertex. It looks like it moved down 3. So in this problem, I have a vertical stretch, or shrink, I guess would be a better way of putting it, of 1/2, and I have a vertical shift down 3. So that's problem 1. Problem 2, f of x equals x squared. If I graph the function by substituting in some points, I'm not trying to pick exceptionally complicated functions to graph here. For the notes, I'm just trying to get us, my fault, those are positive. I'm just trying to get us to have an awareness of what's happening. So there's the parabola. Now, if I look at this function, f of x in this problem is x squared, so I can replace this essentially with some kind of x squared graph. So this is going to be y equals 2 times x plus 3 squared. So notice that x plus 3 replaces x in the function. That's what we learned in the functions part of the unit. So 2 times x plus 3 squared plus 2. So if I plot points, I'm going to do a little bit of trickeration right now to make sure that things go smoothly. If I put -3 in, that becomes 0. 0 squared is 0, times 2 is also 0, plus 2 gives me 2. If I substitute in -2, what happens is I get 1 squared times 2 plus 2, so I get 4. If I substitute in -1, I get -1 plus 3 is 2. 2 squared is 4. 4 times 2 is 8. And then when I add 2, I get 10. In the interest of time, I'm just going to tell you that those points also work. So -3, 2, -2, 4, and -4, 4. And then likewise, these points would be off the graph somewhere. So there's my parabola. Now I could also look at this in Desmos if I want. So that might be a good idea for you to check that on desmos.com and actually type this in and see how it relates to the original function that we had on a little bit better graph. But basically what we found would happen from our notes earlier is that the first two should be a vertical stretch. And that makes sense because if I look at the typical graph, it would look something like this. So what I'm noticing is that my my red graph, the actual graph of the function, is more narrow. That makes sense because that means it's getting stretched out. My y values are increasing faster. The 3 in the middle is a horizontal shift, and I know that that's going to move left 3. So notice that my vertex moved to the left 3. Also, I have a vertical shift up 2. Notice that my vertex moved up 2 as well. So if I describe the transformations, I have a vertical stretch of 2, a horizontal shift left 3, and a vertical shift up 2. Finally, if I graph y equals square root of x, in the interest of time, I'm just going to plot the points. That'll look something like that. This function would be the same as y equals negative square root of x minus 1 minus 4. What we would assume, based on our notes, is that I'm going to have a right shift of 1, a down shift of 4, and this a value is negative 1, which means that I would assume that it doesn't really stretch or shrink at all, but it does. Spelling is important. It does flip over some sort of horizontal line, which oftentimes is the x-axis, but in many cases it actually flips after we, actually in almost every case that we do, it flips after we move the most important pivot point of the graph. So if I just take a look at what's happening, I'm assuming there's a right shift of 1 and a downshift of 4. And then instead of this graph moving up, I would assume it moves down. So it would look something like this. Those are just my assumptions. So I'm assuming the point 1, negative 4 is on the graph. If I substitute in 1, I get negative 4. I'm assuming the point 2, negative 5 is on the graph. So if I substitute in 2, I get negative 5. And I'm assuming the point 5, negative 6 is on the graph. Based on my graph, when I substitute in 5, I get the square root of 4, which is 2. And then negative 2 minus 4 is negative 6. So my assumption was correct when all of those things happened. Therefore, if I describe the transformations, I have a vertical flip. I have a vertical shift of down 4. And I have a horizontal shift to the right 1.